Good morning, and welcome to the Virtual Summit, Technology and Solutions for Next-Gen Communication Systems, brought to you by CTS. I'm Graham Kilshaw from Lectrix, and I'm delighted to be your host today. I think it's safe to say that 5G and IoT are going to change the way that the world communicates quite radically. 5G is not just an incremental improvement on 4G, as we all know. It's a whole new cellular network strategy. 5G will allow much faster transmission of data and provide the capacity for the explosion of cellular devices we're seeing in the world today. IoT, once famously referred to as allowing your refrigerator to reorder its own filter, will do much more than that. Cars and machines of all kinds will be able to communicate with each other. It will create a whole new approach to safety in cars, factory equipment, and homes. And IoT is going to enable industry like never before. 5G and IoT will be entirely new and exciting networks. But like any chain, they can only be as strong as their weakest link. Every component and device in the network must enable precise and accurate transmission of the signals. And so today, CTS is going to help us to take a look at two of the key aspects of these new networks: timing and filtering. But before we kick off the first webinar, I'd like to take a quick second to send a special thank you to Richardson RFPD for sponsoring today's event. So now, without further ado, let's get started. The title of the first presentation today is IoT, Demand for Timing at Low Power. And I'm going to hand things over to the first speaker, Ronan Cohen. Ronan is the Senior Product Manager of Precision Timing and RF Devices at CTS. Ronan, over to you.
Welcome to CTS's webinar for frequency control products supporting enhanced IoT designs and solutions. My name is Ronan Cohen, a Senior Product Manager at CTS managing frequency control products. In our discussion today, we will address a few topics. We'll start with an introduction to IoT along with opportunities and challenges. Then we'll move into some of the markets and applications that evolve. We'll address some of the protocols and the standards that define the requirements for performance and communication between different devices within the IoT space. Then we'll look at some of the technology that enables operation under low power, specifically with battery-operated related applications. And then we'll have more specific application examples and how timing affects the operations. We'll move from there to some of the solutions that currently we offer at CTS for IoT market, product availability, trends, and we'll wrap up with a conclusion. Internet over Things is an evolving platform allowing connectivity of live information between control mediums and gateways or clouds to wireless devices. Currently, there are already billions of devices connected over that platform to smart homes, smart intersections, factories, healthcare providers to their patients over cloud, some agricultures or smart grids as an example. As 5G networks will evolve and allow higher speed of connectivity, the number of connected devices will increase exponentially. On the challenges side, some of the existing or new components that are coming up, like microcontrollers, SoCs, FPGAs, require much lower noise operation, and therefore the components that surround those devices have to withstand similar types of attributes. At the same time, a lot of devices are expected to operate under battery power, and therefore low power consumption is very critical. We're also expecting to see multiple communication protocols and consequently different timing standards between different devices. So therefore, there are different requirements when it comes to frequencies, different requirements when it comes to power, and we will talk about some of the offerings that CTS have for such requirements. As we approach IoT applications, we have to address a couple of challenges. The first one has to do with power consumption. It is expected, especially in smart homes, that number of the devices, the connected devices, will be battery powered. So therefore, the design of such devices have to support low power consumption. So standards like Bluetooth or Bluetooth Low Energy have to be considered along with low power consumption type of MCUs or RFICs to be able to sustain operation for a long period of time with the same battery power. On the other hand, in some cases, we're expecting to have an increased number of devices as 5G networks will enable more and more connectivities of multiple numbers of devices. So it's very critical to, one, address compatibility of such devices so they can communicate between each other, as well as eliminate or limit some of the interference. So standards like LORA or Zigbee RF4CE will allow, one is limitations of interference or the compatibility between those type of components or devices. As we move to Industry 4.0, we're expecting the amount of information transmitted from the controllers to machineries or types of equipment is going to be increased. So there's going to be more information transmitted from each piece of gear to the clouds and to the controller. So standards and ability to sustain and to support the amount of information is very, very critical. Internet over Things enables functions and operations for single devices in real time through standardized communication protocols and timing standards. As an example, we can take a sensor and an actuator that over IoT platform will communicate with each other. At the same time, they will be communicating to their controlling entity. That controlling entity is communicating back to a cloud that captures the functions and operations. A user can access that cloud in order to monitor and review some of those operations. The entire platform is being deployed utilizing wireless and wireline type of mediums, where the wireless medium enables flexibility from deployment locations as well as cost to be able to access these operations at a very high speed and high efficiency. Here we can see two examples of how the different layers operate when multiple devices communicate with each other. We can see the devices portions that are pretty much the user type of devices that communicate with the cloud. That cloud communicates with a gateway that controls some of the sensing and actuating type of devices, whether it's cameras or type of locks, lightings, thermostats, and so on. When it comes to industrial type of applications, now instead of controlling small devices, we're talking about machinery, We're talking about data center that capture a lot of the information from all this equipment and then makes operation accordingly. So essentially, we're looking at three ways of communication: device to device, device to a gateway, and then a gateway to some cloud or data center that capture all the information. The ability to transition to wireless communication is highly desirable, primarily for flexibility and cost. But that comes obviously with some challenges, primarily in terms of compliance to the standards and protocols that given device must comply with. On the left table, we could see some of the ranges of protocols that a given device must comply with. As an example, the low power wide area network, here we're looking at a range of 1 to 3 miles range, where a spread spectrum technology at low power is being used. As we go into smaller range or shorter range type of communication, now we're resorting into protocols like Zigbee, Wi-Fi, Bluetooth, etc. And in very long ranges, cellular infrastructure can assist with the communication. On the right table, we can see some of the bands and the distances along with power and cost that are involved with each of the technologies. So it's very critical to deploy, obviously, a network or a platform that will use the right protocol, but at the same time will not create any interference or some collision between the different protocols such that they will interfere with each other. As technology evolves and requirements for designing systems that must comply with protocols and standards are tightening up, designing such systems at a cost-effective manner as well as in time to market while complying with such standards is becoming more challenging. And we're seeing more and more semiconductor manufacturers that coming for help by designing a lot of those building blocks right in one single chip. Here we can see a device that was designed for IoT platform, and it encompasses building blocks that include security, it includes the energy management, it includes all the computing and the processing power, as well as the blocks that relates to the radio that control the noise and transmission of the data between the different devices. Where CTS come into play is with the timing block. CTS connects and work in collaboration with such semiconductor manufacturers by qualifying and designing timing devices. And in a case of IoT, we're looking at crystals and specific clock oscillators that will comply and will be qualified for such devices. As we address timing for IoT platform, and in particular IoT chipsets, we will also look into the wireless functionality of this system. Now, we know that any radio will have a transmitter and receiver, and timing devices are pretty much the clock generators for the entire chipset and the entire functionality of the system. So we also address the fact that such devices, for the most part, will be battery operated. And in order to maintain longevity of the battery power, it is designed and it is desired to run all the components within the radio at low power. So that means that in order to also drive the timing device, and if it is a crystal, then the oscillator portion sits within the chipset, and it drives the crystal with a certain driving power. And given the fact that such system is designed to work also with low gain margin, such crystals will have to be designed with what's called low ESR, or low series resistance, and low shunt capacitance. That will allow a quick startup and also preserve some of the energy. In addition, we're seeing different grades of IoT type of devices. In cases where consumer type of applications or low-cost type of applications will have to be deployed or designed, it's also very critical to select the right components as peripherals to drive the correct chipset. Normally, crystals are considered to be the lowest cost type of devices for timing. And in such cases, obviously, crystals will be the selected components to drive the entire radio, the entire device. In other cases, the complexity of such devices is becoming a little bit more demanding, and higher accuracy or lower noise are desired. And for such situations, there's a way to select low noise clocks, low jitter clocks, or TCXOs that will maintain the high stability in case that there is a need to be steered by a GPS or other system reference. As we talk about the timing block of the chipset, I'd like to bring some insights as well as suggestions as part of the integration of the crystal or any type of resonator into the circuit as part of the peripherals. So at first, most chipsets use what's called Pierce oscillator to drive a resonator. A Pierce oscillator is pretty much constructed with an amplifier that runs a certain driving power through the resonator, and through a 180 degrees phase shift and the load, we're creating the oscillation. And the frequency that that particular resonator was designed to work at will start oscillating. Now, the key portion of the integration is selecting the right load capacitance that will also allow that correct feedback and the right oscillation. So at first, you want to go back to the reference design documents from the chipset manufacturer to select the proper load capacitance. It's very important to select combinations of two capacitors, as you can see in the bottom figure. However, when you select those capacitors, you also have to take into consideration your PCB layout. Given the fact that in high frequency and AC, any trace is not just a short. It has a certain characteristic impedance, and it will have attributes of a transmission line. The higher the frequency, the higher the contribution of the characteristic impedance to the overall load. So when you characterize the length of the trace and the thickness of the copper within the trace, you will have a certain characteristic impedance at the frequency of oscillation. Once you define that, you select the proper capacitors that altogether will create a certain load on the resonator. That will ensure that not only you have the proper gain margin, but also that you're calibrated to the resonant frequencies at the tolerance that the chipset is required. As we address low power requirements for IoT platform or IoT devices that are battery powered, I'd like to take a step back and discuss some of the low ESR capabilities that crystals will offer. So in these two figures that we see at the bottom or in the middle of the slide, you can see on the left-hand side a quartz crystal, and then on the right-hand side, the equivalent circuit of a quartz crystal. So when we look at any type of resonator, we are, in a particular quartz crystal, we're talking about a resonant circuit. In a case of quartz crystal, we're talking about series resonance, and together with series resonance, there's three major components: capacitive, inductive, and resistive elements that are required to generate a certain resonant frequency. In addition, and that basically defines the resonance of the quartz itself for the case of quartz crystals. Then we have to mount that quartz onto a certain package. Given the fact that we're talking higher frequency, any connections, any mounting structure will have some characteristic impedance. That characteristic impedance is being defined by C0. In a case of low gain margin type of circuitry, where the driving power is very low, we want to make sure that R1, or the resistive component, and C0, the shunt components, are kept to a minimum. And that will ensure two functions. One is quick startup when we look at wide temperature range. The second attribute that it will guarantee is maintaining and retaining battery power for a long time. As we address low power requirements, I also wanted to discuss some of the impact of low power on the resonance and the crystal. Think about the crystal as pretty much the engine of that particular system. If you don't give it enough fuel, any disruption, any imperfection within the structure will have some impact on the oscillator, or the oscillation for that matter. Now, given the fact that quartz is an electromechanical device, piezoelectric, it transforms mechanical energy to electrical energy. With that, if there are any imperfections and the power to drive through those imperfections is not sufficient, they will be very visible in the applications in forms of frequency jumps. So, before we qualify a certain design, in order to guarantee that those frequency jumps are not becoming apparent, we're doing what's called DLD, or drive level dependency test. In such test, we're basically varying the power level and we're looking at the changes of resistance. If we see that as we increase the drive level, we see a smooth change of response from the crystal in forms of resistance, we know that pretty much the imperfections are kept to minimal and they're not going to be contributing at all or not going to show at all within your system. But if we see specific jumps, we know that those transitions or those changes may translate to some frequency jumps, and with that, we disqualify such crystals. Every single crystal that is being shipped out is going through this drive level dependency test. Also, the impact of contaminations, given the fact that quartz crystals are being manufactured in a clean environment, any type of contamination will have impact both on the startup as well as some of the long-term stability of the device, what we call aging. We do what's called accelerated aging tests, where we relieve all the stresses from the mounting of the quartz on the package. But we want to make sure also that the process of manufacturing of such crystals is clean enough such that the imperfections, the impurities are not going to become apparent. And like I said, the fact that we're running the entire resonator at low power, such imperfections, such impurities will have impact if they're not being carefully screened and taken care of in the manufacturing process of that particular crystal. As we have addressed thus far, the IoT platform as a whole, some of the protocols and standards that it deploys, along with the requirements for different as well, timing in particular here. I wanted just to bring up a couple of examples that show how timing devices are being integrated in various systems. The first example shows a smart home application, a security system for that matter, utilizing a TI chipset. So as you may expect, cost, size will probably be a very key element for any component that will be integrated within the system. So when we look at the timing devices, there are pretty much two required timing devices here. The first one is for timekeeping, a 32.768 kilohertz type of device. In this case, you would more or less will get a stability of plus minus 20 ppm on the tolerance and stability of plus minus 150 ppm, minus 40 to 85. Key attribute is obviously the low ESR that will allow and enable quick startup and low battery power or power preservation. On the main timing portion of the device, we're looking at a 40 megahertz crystal that is running with very tight tolerance, plus minus 10 ppm in room temp and plus minus 10 ppm over temperature. And again, with low ESR that will allow same attributes as the timekeeping crystal, quick startup and power preservation. This particular device is sized at 2 by 2.5 millimeter to allow small size and also to guarantee the performance. The second example addresses an industrial type of application. Here we're talking about smart agriculture area, RFID for tracking cows and cattle. Because of the fact that here we're talking about bigger distance between the gateway or the controlling unit and the actual devices, we're using LoRa type of standard or protocol. So here we don't have the timekeeping function needed, but we do need obviously the frequency for the transmitter, for the radio. So every unit will get a 32 megahertz crystal with tight tolerances, plus minus 10 ppm at room and plus minus 15 ppm over temperature. This device is running at 2 by 1.6 millimeter size. So obviously the ESR is slightly higher than the previous example where we were running at 2 by 2.5 millimeter, and also the frequency is lower. So we expect the ESR to be slightly higher, but still low enough to guarantee the power preservation and startup. The third example also shows a commercial application. This time it's a diabetes monitoring device utilizing a TI chipset. And here, just like with the first example, power preservation is a key attribute. So we're looking here again at a 2 by 1.6 millimeter size. Only single crystal for the transmitter, 24 megahertz, again with tight tolerances, plus minus 10 ppm and plus minus 15 ppm over temperature, with low ESR below 60 ohms. And the tight stabilities and the ESR, along with the size, are the key elements for integration within this small type of a device. Thus far in our discussions, we have addressed some of the requirements for the IoT platforms. We talked about some of the challenges when it comes to power conservation, when it comes to noise, when it comes to cost and size. So when it comes to the timing devices, we have grouped the product portfolio into 3 major categories. The first one is the enhanced crystal group. These are the type of devices that will trigger the transmitter and will have different frequencies, but also they must come with low ESR to guarantee the low power consumption. In the second group, we're talking about the tuning fork that are pretty much used for timekeeping. And they also, part of the enhanced crystal, have to be maintained at low ESR in order to operate properly with low gain margin that also guarantees the power conservation. And then for systems that have to lock to GPS or enhanced type of reference, a local TCXO allows a quick locking time and also some of the filtering of the noise that comes from those references. Now, as we expand the discussion over the product variety between the different groups, we can see that different applications may require different starting frequencies from the timing device. And we need to keep in mind that the entire platform of IoT is still evolving, and this is a very specific snapshot of common applications with common frequencies. We expect that as the platform expands and more applications will come about, new chipsets will come about, this list of frequencies is going to expand and increase. So if we go to the left column of the tables, at the top we can see the enhanced crystal group. There we're looking at the frequencies that part of the right-hand table will be supported, from frequency ranges to size, stabilities, operating temperature range, and very critical attributes like ESR and shunt capacitance. In the second group, the frequency of the tuning fork is obviously a fixed frequency, 32.768, but then you still have some selection when it comes to the packaging. With respect to the packaging, there's also going to be some variance to the attributes like the ESR and the shunt capacitance, where the stabilities in the temperature range remain fixed. When it comes to the real-time clock TCXO, obviously size is one of type of offering, temperature range, stability, but then you do have an option when it comes to the supply voltage. We encourage you to visit our IoT landing page where there's more details when it comes to the product specifications and some of the attributes for the IoT specifics and the requirements. Product availability is done through the distribution channels. For our NPI lots, we have selected DigiKey and Mouser. As mentioned in my previous slides, we have selected only specific frequencies that are considered to be more standards. However, we do encourage you to go to our CTS stock check tool and basically look into the specific product, the specific frequency that applies to your design, to your chipset. If you do not find the specific product, please feel free to contact us and we will address it on a case by case. When we look at the tables here, you could see on the left-hand column within every table the specific part numbers, and on the right column the attributes that apply. Being that IoT is an evolving platform, we're seeing new trends and new directions that are taking place as the technology evolves. As an example, industrial IoT or IIoT is one area that is expanding when it comes to improvement of productivity, automation, and obviously some of the monitoring of systems and processes. The more applications and the more demand for information to be transformed from one location to the other, the bigger the bandwidth or the higher the bandwidth that is required from the systems. So you can see that areas like Bluetooth 5.0, Wi-Fi 6.0 are starting to take place with new spectrums, with new modulation schemes that allow higher speed of connectivity. Also, the fact that we're expecting more from our devices to operate longer periods of time under battery power, we're expecting more devices to operate with components that consume less energy. As we have seen in the mobile phone area, where Apple and Google came each with their own platform. We're seeing a similar trend also in smart home automation, where big companies like Amazon, Apple, and Google create their own platform and protocols where devices have to be able to comply with in order to bring up and bring down some of the information. So intercompatibility is a very big challenge that has to be addressed in the design area. Also, the trends where our internet was and still is being acquired through hardwire, whether it's a coax, a fiber, a twisted pair, is being transformed into wireless access network, where essentially we will access our internet wirelessly rather than through a wireline medium. Areas like bandwidth, as we talked before, is a key. The pipes are obviously being more and more jammed with higher demand for information. So networks like 5G, millimeter wave, and obviously at the user end, such as IoT, have to be all compatible such that the information could streamline from one user to another through the transporting networks. In areas of vehicle and automotive, new cars are becoming the new hotspot for another area of information. So, for example, new cars today, you can get them with Wi-Fi hotspot. And with that, even applications within the vehicle communicate with each other and with their gateway wirelessly. All that to eliminate the cabling and the wire harnesses within the vehicle. In conclusion, as we've seen in our discussion, Internet over Things is an evolving platform. It offers new applications and with that new opportunities. But at the same time, the requirements to move to higher frequencies and higher modulation rates brings with it new challenges. New protocols and new standards are put in place in order to guarantee smooth operation. And with that, new chipsets, new peripheral components have to be assigned and have to be deployed in order to guarantee such high performance. When it comes to CTS, CTS has been in the timing and frequency business for many years. And our effort to focus our product offerings to specific applications with the attributes required is paramount. In this case of the IoT platform, we already talked about low power consumption, lower noise. We talked about size, cost, and availability as key elements to support and enable you as designers and manufacturers of devices within that platform. So when it comes to some of the information that we're offering, you can see in this slide there is a list of website links, and these are all available on CTS Corp website, from IoT landing page to 5G landing page, along with white papers, selector guides, and stock check tools to utilize and use as you design your product. For the quality area, REACH and ROSE certifications are also available on our website. So please feel free to access this information and let us know if some of the information that you're looking for it may not be available online. We'll be more than happy to assist you. I wanted to thank you once again for participating in our IoT webinar. And now we'll move into the Q&A session.
Thank you, Ronan. Great presentation. Yeah, let's move right over to the Q&A. Very interesting presentation. And today, Ronan has his colleague, John Metzler, with us to answer some of your Q&A. John is one of the applications engineering team at CTS. And so, members of the audience, there's a Q&A button at the bottom of your screen. So please just click that and enter your questions now. And we've got several minutes available for Q&A. Whilst you're filling in those questions, there's a couple in there already. Let's jump right over, Ronan, and take the first one. This first question is, from your experience, does the communication speed or transmission power of a specific IoT device affect the timing requirement?
Thank you, Graham, and thank you all. Basically, the main heart of any device within IoT is driven by chipsets. As we know, there are multiple chipsets out in the market, and depends on the protocol that the device or that chipset is being designed, and that device will dictate what kind of timing it will require. It's obviously, we talked about noise, so noise requirements are very critical, power is very critical, so the amount of multiplications will be also part of the areas where we need to take care of, and we need to make sure that are minimized in order to preserve the noise accumulation and also the power generation, the power consumption. So in such cases, what we will see is that the chipset manufacturers will give guidance with respect to the timing requirements, frequencies, ESR, and even areas like shunt capacitance to ensure correct performance. So I would expect that there might be some variations on the crystal attributes, but also we need to make sure that you guys are, as designers, are following what the application notes define.
Okay, great. That's pretty clear. Quick housekeeping question before we move on to the next question. Somebody's asking, will we send out the presentation? You can download the presentation slides from one of the links at the bottom of your screen. You can also re-access it through the email that you were sent with a link to this presentation. So that's all automatically available. And you'll be able to watch the on-demand version of this presentation, the recording of it, if that's what you'd like to see. Give it a couple of hours for the file to load, but certainly by the end of today, you should be able to re-watch the presentation or share it with some of your colleagues. Okay, so let's go on to the next question. So Ronan, this question says, out of your IoT crystal offerings, are there any considerations other than size that an engineer should account for when they're selecting one crystal model over another?
Yeah, so as I mentioned, a lot of the recommendations come from chipsets, the chipset designers, and so they do a lot of the work as they qualify some of the timing devices, and they will define what are some of the characteristics that they require in order to comply with the performance that they need. And I also will let John, if you have a couple more comments on that particular question, feel free to add on to that.
Okay. When you're looking at the various models that we have offered in the table that Ronan had shown in the presentation, ESR will be one of the largest factors in determining the package size that you can use in your application. As the package size gets smaller, the ESRs tend to get larger, and therefore the limitations may be there for going very small because of the ESR that you may need in your application. Also, the frequency on the low end will be a factor when it comes to package size. Again, as the smaller package trend gets smaller, the frequencies on the bottom end of the range get larger. So if you're looking for something in 10 megahertz, you won't be able to find that in the smallest package size we offer. You would have to go to something like a 3.2 by 2.5 millimeter to satisfy that frequency. So those are probably the two key parameters that will drive you to a given package size.
Okay, thanks, John. Any more questions, folks? Now's your chance. Ron and John, before we wrap up, are any other comments you'd like to make before we get to the end of this presentation?
I mean, from my side, like I said, I mean, this is an evolving platform, and we're going to see more and more changes and more add-ons to frequencies, requirements, especially when it comes to power, when it comes to performance under low gain margins of some of those chipsets. So I hope that some of the overview that we've been showing here kind of give an idea of how we see it from our end. And we definitely welcome any questions, even if they're not right now. Feel free to contact us and let us know how can we make sure that we support some of the new requirements as you come about the applications, as you come about new designs of chipsets. We'll be more than happy to support such activities, especially when it comes to either reference designs or supporting specific application, specific designs on a case-by-case. And
okay.
Once again, I wanted to thank everybody for taking the time and joining us here today.
Yeah, we had a good audience today. And Ronan, John, what's the best way for folks to contact you after the presentation?
So in our website, is the invite of the session. There is my contact information, the email address, as well as phone numbers, and we can possibly also add it to at the end of the presentations to make sure that people are able to contact us. So not a problem.
And I'm sure you can be found on LinkedIn as well. Lots of ways to contact you. Okay.
Yes.
Ronan, John, thanks very much. Great presentation to start the CTS Virtual Summit on 5G, IoT, and the cloud. This is the first presentation of the day. The second one is coming up shortly. If you've not yet registered for Ronan's next presentation, which is 5G millimeter wave systems and noise consideration, that's coming up very soon. Just go to the CTS website to register, or go back to one of the emails you've received. That will be starting shortly. My name's Graham Kilshaw. I hope you enjoyed the first presentation, and we look forward to seeing you again very, very soon. Bye for now.